Okay, hello biology people. Gonna finish up our bonding with this discussion here, chemical bonding. So up to this point, you should be familiar with two types of bonds. First, the ionic bond, the attraction between cation and anion. We look then at the idea of a covalent bond. So in the covalent aspect, we have no oxidation, no reduction. We have then the sharing of electrons. Once we have sharing, we have to then analyze, is it an equal sharing? Is it a non-polar covalent bond? Is it a unequal sharing, a polar covalent bond? And we have to then understand the sort of the strengths of electronegativity in order to help us understand polarity or non-polarity. So that kind of leads us then to the third and final bond that we're going to cover this semester, which is the hydrogen bond. So hydrogen bonds are presented third in the sequence because they have similarities of both prior bonds, and they have certain qualifications that have to be in place first. So first off, we must have a polar covalent bond. So there has to be a sharing of electrons, an unequal sharing of electrons, polar. Once we have a polar covalent bond, the stronger electronegative element will get the delta negative charge. The weaker electronegative element will get the delta positive. So we have one molecule. On one side is going to be delta positive. On the other side will be delta negative. Delta negative on the strong, on oxygen or nitrogen. On the carbon or hydrogen, we would have a delta positive on the weak. So if we have a non-polar covalent bond, we don't have this discussion. There's no hydrogen bonds. Again, if it's a non-polar covalent bond, hydrogen bonds cannot form. Yeah. So we must have a polar covalent bond, which generates unequal sharing, which within the same molecule presents a delta positive and a delta negative on either side of the shared electrons there. So once we have that, we can then discuss our hydrogen bonds. Right? So these are very, very weak bonds, and they're going to be that same concept of opposites attracting, kind of like ionic bonds, but it's a very, very weak, very minimal attractive force between a delta positive of one molecule and a delta negative of another molecule. So, here. Yeah. So we deal with water a lot, right? Water is a very important, very ubiquitous molecule in biology, and it has a lot of significance because it is sort of constructed of a polar covalent bond here and another polar covalent bond here. So generating our delta negatives on the oxygen, delta positives on the carbon. Now, if I was to put multiple water molecules together here, right, we tend to see an interaction, right? So this is within one molecule. This is within the other molecule. And then this attractive force is between the two molecules. So the hydrogen bond is this opposite attractive force between different molecules, right? So a lot of little distinctions there, right? It's not the same as an ionic bond. There's no oxidation, there's no reduction. We're sharing covalently, polar covalently, generating delta charges on either one. And we have that strong bond for better, for worse, in sickness and in health in here. And then we have this sort of extracurricular interaction with another molecule outside there, right? So looking at this little dotted line, when they symbolize little dots like this, that represents an attractive force between different molecules, the attractive force between a delta negative and a delta positive, right? So delta positive and delta negative, delta positive and delta negative and delta positive here. So again, so instead of having 1, 2, 3, 4, 5 different molecules, we still have 5 different molecules, but they function as one singular unit, right? If I get this top one and I just gently move it to the right, all the other 4 will move to the right with it because they're all bonded together. But they're not strong bonds. We can break those bonds, but there's a bunch of them. And if I put maybe one staple on some papers, it holds a little bit. But if I start to put a bunch of staples, the more staples I put, the more sort of strength it generates, it holds together. So the more hydrogen bonds that occur, the more additive that strength becomes, right? So it starts to generate more strength in holding these big molecules together, multiple molecules together. So they do have profound biological importance in that regard. So different molecules, right here we have a water molecule, H2O. And here we have something called ammonia, NH3. We have a weak hydrogen bonded with a strong nitrogen. So I hope you remember what charged nitrogen would generate. It would generate a delta negative. Here we had a weak hydrogen with a strong oxygen. So this hydrogen in water develops a delta positive. So delta positive on the hydrogen, delta negative on the nitrogen allows these 2 different molecules to draw together, form that little weak hydrogen bond, symbolized by 3 little dots there. And again, this qualifies for the idea of a hydrogen bond. So important in biology. They're all over the place. All these extracurricular activities we see a lot in the chemical world there. Yeah? And again, this is only possible if we generate delta charges. If there's no delta charges, we don't have any opposites to attract. So that stabilized nonpolar molecule just stays by itself, right? So does not hydrogen bond with anything else. So I really want you to analyze this sort of chart. It's got some other stuff that we did not get into. Don't worry about hydrophobic interactions, van der Waals forces. We didn't get into those, but you are responsible for the first 3, right? Covalent bonds, hydrogen bonds, ionic bonds. So be sure and know what they are, how they form. Again, the what, the how, the why, the when, the where, that kind of stuff. So we started first with ionic. So what had to happen first to generate ionic bonds? We had to stabilize to form a cation by oxidation. We had to, a different molecule, or I should say a different element or ion or molecule had to stabilize by the process of reduction. And that full anionic and cationic charge then allowed us to, follow the laws of physics, opposites attract, forming the ionic bond between the different molecules here. Covalent bond, we then formed by sharing electrons, so no oxidation or reduction. We could have polar covalent or non-polar covalent. If we have polar covalent, then we can progress to hydrogen bonding. And I hope you see some similarities here, right? So we have opposite charges between delta positive, delta negative. We have the bond between the different molecules, but here we see like little dots. Here we see like this shaded area. Again, the ionic bond would be complete ionic charges, so it's a little stronger. We say it's about 7 kilocalories in strength. The hydrogen bonds tend to be about 3, so they're very weak. And then the covalents, depending if it's a single, double, triple, can be 50 or higher. So it's a much stronger type of interaction. So with that will conclude then our discussion on bonds. And I would then like you to continue onwards, and we'll get through the water, functional groups, acids and bases, chemical reactions. So it's a lot of stuff to cover in chapter 2, but we'll get it done. And with that, I'll call this one complete here.